All right, so let's get started. So this is a lecture for March 26th, Thursday, before spring break. So this is a continuation of our discussion about Cesaro summability and the Fejer kernel. So this is a new way interpreting the convergence of a Fourier series to original function. So let me remind you what we did on Monday and then what we are doing and why we are doing this stuff. So the main theme of this course is a convergence of Fourier series that we want to decompose the periodic function by sine and cosine. If every function can be written as a sine and cosine, sum of the sine and cosine, then many problems can be solved easily using the property of sine and cosine. So that's the basic idea of a Fourier series. But unfortunately, this is not the case that naively we think that we define, so let me see, we define the partial sum of Fourier series. So this is a partial sum of the Fourier series. So that the index goes negative n to n, f hat n, e to the I n x. So this is a partial sum of Fourier series. What you want to do is that if n is the function is a continuous, so that we can talk about the function behavior, pointwise behavior that at that location, how the function behave, then something we want to say something like this. Does if f is a continuous, then the partial sum is a converges fx as n goes to infinity, right? So this is some question that we want to answer. The answer is no. Unfortunately, answer is a no. We'll see later that there exists a continuous function such that SNF, the partial sum, does not converge to the fx. So this notation here is a does not converge. Right? So not every continuous function has this a nice property that the Fourier series converges the original function. We have seen some sufficient conditions. The right now remark is that we know some sufficient conditions for the convergence. Fx to fx. So this is x. So what's the sufficient condition that when the Fourier series is absolutely convergent, then we know that the Fourier series and then function is a continuous. If the Fourier coefficient negative infinity, infinity is finite, and function has to be continuous, and f is a continuous, then this convergence happens. S and fx limit n goes to infinity is fx. Okay, so this is a one remark. And the another remark is obviously then we want to ask when this condition holds. This condition holds in particular when f is a second differentiable. If f is a C2, then f hat n is bigger 1 over n squared, meaning that f hat n is a n most 1 over n squared for large n. So, and then we know that sum n is a 1 to infinity, 1 over n squared is a p series with a p equal to 2, which is bigger than 1. So then then this condition satisfies. It's a basically summation, some constant to it's a finite. Okay, so if in short, if f is a C2, then Sn fx converges to fx. All right, and then this convergence is a uniform. So this is what we have discussed so far. And then the disadvantage of this condition is a function has to be second differentiable, which is a very strong condition. So, intuitively, we should expect that when function is only continuous, then the function has to converge in some sense, right? So this is the what we are right now. So let me see. Let me see if I can see how much time has left. So let's see. I don't really see how much time has passed. Okay, let's continue. Right, so let's see. So we wanna we wanna somehow talk about the convergence of a Fourier series when a function is only continuous. Then we know that this is not true. So the idea is we will interpret the sum in a different way. So that is a Cesaro. Let me see. What's the spelling? Cesaro. S-E-C. Cesaro convergence. Cesaro convergence. Sorry about that. So Cesaro convergence is a new way of interpreting convergence of a Fourier series. So Cesaro convergence is that instead of having the convert the sum itself, we take the average of the sum. So idea is that we take the average of sums. We take the sums, we take the average of the sums. We sum those sums. We sum them up together. We take the average twice. So we have seen that the one average is not sufficient enough, that there is a continuous function whose Fourier series does not converge. But if you take the another average, we take the average of average. Every time we take the average, then it makes the properties nicer. So that the Cesaro convergence of a Fourier series happens. So that's the what we discussed last time. And there we talk about the Fejer kernel. So that's the what we want to do. We discussed on Monday. What is the Fejer kernel? So let me remind you. So this is a partial sum of Fourier series. So this is a n is a negative n to n, f n, e to I n x. And by this sum can be written as the convolution of Dirichlet kernel with the f, where the n x is nth Dirichlet kernel, which is just this quantity. All right. And then we have seen this is given by sine x over 2 sine plus 1 half of x. All right. So this was the Dirichlet kernel. So this is the direct sum of we take the sum directly in this way. And then we wanna take the sum different way and then think about the Cesaro convergence. Cesaro convergence is an average of average. So what's the Cesaro convergence? So we think about the sigma n fx. So this is the Cesaro mean, which is defined as we take the average of S0 fx plus S1 fx plus dot 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 plus Sn minus 1 fx, right? So Sn is the partial sum of the Fourier series. So we take the partial sum and then we take it average. So this is like an average of average. We take the average twice. Okay. And because this is given by, think about this. This is a 1 of n. So this is a D0 combo. So let's see. D0 convolution fx plus dot 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 plus d n minus 1 convolution fx. And the convolution is linear so that we can write this as 1 of n d0 plus d1 plus dot 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 plus dn minus 1. Everything convolution f of x, right? So that we denote this as fn x, which is Fejer kernel. So this is a definition of a Fejer kernel. This, let me do it again. The Cesaro mean f can be written as the Fejer kernel define convolution with fx. So Cesaro mean of f, this is a average of average, and this is can be written as convolution of a Fejer kernel with f, where f and x is the average of Dirichlet kernel. Okay, so this is what we discussed on Monday. And what do we want to do today? The goal for today is a two topics. Oops. The first goal is that we are going to show the Dirichlet kernel can be written as a sign, and then the Fejer kernel also can be written as a sign. So we are going to show that the Fejer kernel has a nice expression, 1 of n sine square x over 2 sine square and x over 2. That it can be written as a sign, and using this expression, we are going to show that fn x is a family of good kernels, so that nice convergence happen. So this is two goals for today. We are going to show this expression, the Fejer kernel, can be written as this nice expression. And the second, using this expression, we are going to show that Fejer kernel is a family of good kernels. Good kernels. What's the definition of a good kernels? There are three conditions on good kernels. That is the intuitive meaning is that this is the average one family of a function which is not too big, whose mass is concentrated at 0. Not too big, and the mass is almost all mass is concentrated at 0. So the three condition is a 1 over 2 pi, integral negative pi to pi, fn x, dx is a 1. Second, negative pi, fn x, dx. The integral of absolute value is less than for some constant for all n. So this is not too big. And the third condition is almost all mass is concentrated in near 0. So for whatever value delta is, this converges to 0 as n goes to infinity for any delta less than 0. Less bigger than 0. So these are three conditions that we are going to prove today. Okay, so let's pass the first topic that we are going to have the closed form that of the Fejer kernel. So let's prove that, show that. Oops. Any n, the Fejer kernel can be written as 1 over n sine squared x over 2 sine squared and x over 2. Okay, so that's the first thing that we are going to prove. So this is a mostly computational. So let's say try to do this. So so first thing is let's think about the f and x. This is the average of a Dirichlet kernel. Right? So we need to know some convenient form of the Dirichlet kernel that let's think about the Dirichlet kernel. So dnx is a Dirichlet kernel which is defined by negative n to the n e to the I n x. All right? So let's use a notation e to the ix as omega. So and this is can be written as summation 0 to n omega to the n plus summation 1 to n omega to the negative n, right? So far so good. So we divide when the index is a positive and negative. So this is just a geometric partial sum of geometric series. So this is 1 minus omega. The first term is a 1 minus omega to the n plus 1. There is a n plus 1 terms. And the second term is a 1 minus omega inverse. The ratio is omega inverse. And the first term is omega inverse, 1 minus negative n. There are n terms here. Okay, good. So let's say reorganize this term. So I want to have the denominator to be 1 minus omega. So this is a 1 minus omega. So we don't need to do anything over here. And then let's multiply omega. Multiply omega over omega, right? So then this is a omega minus 1. Then this is a, we multiply omega. So this is a 1 minus negative n, right? So this is 1 minus omega, capital N minus 1. This, the sign is a change it. So this is something like this. So this is 1 minus omega to be negative n, negative omega n plus 1. Okay, so this is the Dirichlet kernel. Dirichlet kernel can be written like this. So let's keep this in mind. Okay, so then Fejer kernel is a average of a Dirichlet kernel. So what we need to do is we need to add this expression. We will add this expression. Okay, so let's keep this in mind. All right, so n times f and x, I just move the n over there. Then this is a d0x plus dot 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 plus a dn minus 1x. So this is a summation n is a 0 to n minus 1 is a dnx. Okay, so far so good. And the dn, what is a dn? Dirichlet kernel. We just argued, we just show that this is a 1 minus omega. This is a negative n plus, that's a minus omega to the n plus 1. All right? So this is from this expression that we have shown that the nx is given by this. All right? So we plug in these expressions over here like this. So this is nothing but the nx, small n. Oh, oops. small n. Okay. So this is this is just a 1 minus omega summation n is 0 to n minus 1 n minus summation n is 0 to n minus 1 omega n plus 1. So this is again the two geometric series. So we can compute the geometric series. So let's compute this. So this is just a computation, and then let's not to try to not to make a mistake. It's a very easy to make a mistake. So let's be careful. So it's a 1 minus omega. So let me first compute this guy, and this is a geometric series. The ratio is a 1 over omega. The first term is a 1 minus the omega to the negative n. So there are this many terms. So this is the partial sum, right? So far so good. Minus, this is a 1 minus omega. And then the first term is a omega, and then it's a 1 minus omega to the n. So the two terms given by this. Okay, so far so good. So this is a geometric series. Recall that what we did is a plus ar plus dot 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 plus ar to the n minus 1. Say 1 minus r to the a minus 1 minus r to the n if r is not equal to 1. The partial sum of geometric series. Okay. So the denominator is a 1 is a 1 minus omega inverse, and the other is a 1 minus omega. So I'm going to make the denominator to be the same. So this is, let's not to make a mistake. So I'm going to multiply omega in both denominator and the numerator for the first term. Then let's let's not to make a mistake. So let me write it one more line so that you don't make a mistake. So this is omega over omega. So this is a 1. So what it does is omega minus 1, omega minus omega negative n plus 1 minus 1 minus omega, omega minus omega n plus 1. Okay, so far so good. So then this is 1 minus omega, another is a 1 minus omega. So the numerator is negative omega plus omega negative n plus 1, negative omega plus omega n plus 1. Okay, so this is what? 1 minus omega times 1 minus omega, omega to the negative n plus 1 plus omega n plus 1 minus 2 omega. So far so good? So let's copy this. So we have this one, okay? So let's combine this. There's a 1 minus omega squared, right? So this is a 1 minus omega squared. And there's a omega is in common. So let's take out the omega. Then this is omega to the negative n plus omega to the n negative 2. All right. So this is omega of 1 minus omega squared times omega negative n plus omega n minus 2. Right? So this is so now here we need to take a look at this. Take a look at this. This can be written. This is a common algebraic trick that if you haven't seen this for a while, then this is like tricky. But this is really, it can be written as something like this. The red part can be written as what? Omega negative n is omega negative n squared. and this is omega n over 2 squared. And this 2 is omega negative n over 2 times omega n over 2. Okay? Right? So this is a little bit tricky. The point is that this expression in the parenthesis is a perfect square. It's a square of the function. So this is a 1 minus omega squared omega, and then omega n over 2 minus omega negative n over 2 squared. Okay, so this is some algebraic computation. You see that again we have this expression, and this expression can be written as this way, right? And this is a square plus b square minus 2 times ab, so which is a minus b squared. So it can be written this way. And then another point is that this omega, let's rewrite this guy. Then this is can be written as let's see, right? The over the top the omega, I'll put it in the denominator of the denominator. I can do this. So then this is 1 minus omega, omega 1 half 2 square, 1 over. So far so good, right? Right? Because omega is a omega square root of omega squared. So this guy is omega negative 1 half, negative 1 over 1 half squared. And this is omega n over 2, negative omega n over 2 squared. All right, so this denominator, let's use a different color. This guy and this guy are equal, right? These green expressions are equal after cancellation, right? So this is equal to omega 1 half negative omega 1 half squared, omega n over 2 negative omega n negative n over 2 squared, right? Remember that omega is e to the ix. Good. So the denominator using the Euler formula is a let me write it one more time. So over 2 negative ix over 2 squared e to the I nx over 2 minus e to the negative I nx over 2 squared. Right? Euler formula says this is a 2I sine x over 2 squared. Numerator is a 2I sine nx over 2 squared. Okay, 2i squared cancels out. So this is a sine squared nx over 2. Denominator is x over 2. So this is an expression for the Fejer kernel. So let me summarize this. So this is a little bit of a long computation that we started with this a Dirichlet kernel. The Dirichlet kernel can be written as this form. Okay, so this is a computation, and the Fejer kernel, n times of a Fejer kernel is this sum. So we plug in this expression here. This is equal to the nx. And then we compute things. This is just a partial sum or geometric series, partial sum of geometric series. So we use this formula that you learn in calculus, MAT 252. And then we go this computation. And there's one place that something happens that this expression is equal to this, right? And again, another thing is this expression is equal to this 3. This blue, green is a all the same. This one, this one, this one are all the same. And now we apply the Euler theorem. So what we have shown is n times fn x is sine squared nx over 2 divided by sine squared x over 2. So hence fn x divided by n can be written this way. So this is a closed form of the Fejer kernel. Okay. So if you have any question about this computation, please email me, then I'll try to reply. So let's continue. The second part is that let's use this formula, this a closed form, to show that Fejer kernel is a family of good kernels. So second goal, the Fejer kernel is a family of good kernels. Let's prove this. So we are going to use this. We will depend on this formula. We just show that Fejer kernel can be written in this way. Okay, and this is also 1 over n t0 x dot 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 plus d n minus 1x. So the first condition, integral square root to negative pi to pi fn x dx has to be equal to 1. Why is it so? This is because that Dirichlet kernel has this property. Remember that Dirichlet kernel 1 over 2 pi negative pi to pi dnx dx is a 1 for any n for the integers. Okay, this is because when this is because this is a very important. So d whatever n dn is e to the negative I nx plus e to the negative I n minus 1x plus dot 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 plus 1 plus e to the ix plus e to the I 2x plus dot 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 e to the I nx, right? This is all the sum of the periodic function except this guy. This one is not a periodic function, or this is a periodic function, but this is a constant function. Everything else has a nice oscillation. There's exactly same amount of a positive part and the negative part. So if you integrate this, what happens? If you integrate negative pi to pi dnx dx, then this is the integral negative pi to pi. Right? And every periodic function cancels out each other except that one, except the constant function 1. Everything else, the integral is all zeros except this one, So it is the integral 1 to pi, so this is a 2 pi, right? So this is a property of a dn. Then how about the fn? Fn is a now we can see this. This is d0x dot 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 plus dn minus 1x. So what's the integral negative pi to pi fn x dx? This is integral of Dirichlet kernel, right? So this is a what? This is a 1 over n. This is a 2 pi, right? The first one is a 2 pi dot 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 plus 2 pi. Every Dirichlet kernel produces 2 pi. So this is what? 2 pi n over n. So this is a 2 pi. So when we integrate the Dirichlet kernel, then this is a 2 pi. So when we normalize it, has to be 1. So this is the first property. So we have shown the first property. Okay, so this is the first property of a good kernels. Second property that we need to show that integral is not too big. Natural numbers. Why is it so? So this is also, so here we are going to use this fact that Dirichlet, the Fejer kernel, sorry about that. Fejer kernel is non-negative. So absolute value of a Fejer kernel is the same thing. So this is the first observation. We can read of absolute value. And then we are going to use another fact that the denominator, Fejer kernel has a sin x, and sin x looks like this, right? And then sin x actually has a very nice upper bound that this y equal to x. Then sin x is below this function. So this is some inequality that sin x is less than x for all x positive. Okay, good. And the sine is an odd function. So if you take the absolute value, then uh, sine, so absolute, we take the absolute value, then this is also true. And so this shows that the sine x by looking at this formula for all x in R, right? By just looking at the picture here that absolute value of a sine x is bigger than sine x. Actually, this is almost strict except at origin. Okay, so what does it mean? That fn x is 1 over n sine square x over 2 sine square n x over 2. But this can be written as 1 over n x over 2 squared sine squared x over 2. Okay, sine is less than 1, so numerator is bounded by 1. So what we can say is that this is less than n x over 2 squared 1, which is what? Nx squared, and the numerator is 4. So the Fejer kernel is bounded above by 4 of n times x squared. So this is good. So what can you say? Then integrals negative pi to pi fn x dx. Now we prove the second property. Fejer kernel is a non-negative, so we can take this out. And this is less than negative pi to pi and x squared for dx, which is finite. We need to be slightly let's see. This is at 0. Then the 0 is a little bit of problem. 0 is a little bit problem. So at 0, that the 1 of x squared does not is actually diverges. So we need to be a little bit careful about this thingy. So this is a no. We don't need this. Sorry about that. So we will come back to this later. So that the second condition is actually much easier. Sorry about that. Second condition, what we need to show is that C, right? For all n. But this is actually very, very easy. Very, very easy. Because a Dirichlet kernel has this property. Fn x is 1 over n d0x plus dot 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 plus dn minus 1x. Right? And then integral negative pi to pi dn x dx is a 1. This is always a 1 because of those cancellation for all n. Right? So the second property, sorry about that. Again, this is a positive part. There's no problem at all because it's a average of a Dirichlet kernel and the Dirichlet kernel as a unit mass 1. So this is 1 of n plus 1 plus 1 plus dot 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 plus 1, which is a 1. Right? So when we integrate the Fejer kernel, the absolute of Fejer kernel, or just the Fejer kernel itself doesn't matter because the Fejer kernel is a non-negative. This is just a 1. So this is a second property that it's a finite. Okay, second property is a almost for free. The third property, let's show that for any delta, we need to show that converge to 0. Okay, so here let's use this property. Fn x is 1 over n sine squared x over 2 sine squared nx over 2. This is nx squared over 4, right? We use that the sine x is less than x. Also, sine x is less than 1. We use these two properties. Numerator sine squared nx over 2 is bounded by 1. Denominator sine x is less than x. Sorry. Actually, we need to be a little bit careful. Okay, we need to be a little bit careful because sine x over 2 is less than x, so this gives us sine x over 2 is bigger than 1 of x. So inequality is actually the opposite. You see, we need the opposite inequality. So instead of using this inequality, but luckily that we have another inequality. So sorry about that. Here, this is sine x, right? So this is a pi over 2, right? Previously, that what we argued is a sine x is x is bigger than sine x. This is a sine x. But sine x is concave, so that it is bigger than this blue straight line. This blue straight line is connecting origin to this point, which is pi over 2 to 1. So what's this equation of the line? This is y is equal to 2 over pi x. Right? Good. So what we can see is that sine x is bigger than pi over 2x and less than x when x is a 0 to pi over 2, right? So what we can say is a sine x over 2, 1 is a to this. Okay, good. Good. So this is what? X over pi. So this is the upper bound. This is the upper bound. 1 over sine x over 2 is less than pi over x. So we can have, so this is a really what we want to know. So this guy, absolute value is a x squared was C1, x squared C2. C1, C2 is some appropriate constant, but this is a comparable to x squared over 1. Okay, so we need this inequality. Remember that this was a what we could get from this inequality, but because we have this opposite inequality that we have both directions. Okay, so so this is what we need. F and x is 1 over n sine squared x over 2 sine squared nx over 2. This is less than 1 over n x squared over some constancy. The actual value is not really that important for x less than pi. Okay, negative pi to pi. Now, the third property is what is this integral? Like the absolute value does not matter because the Fejer kernel is a non-negative. Then this is a delta x pi. Let's use this upper bound. This is a nx squared over c dx. So this is constant over n. This is a delta to infinity dx over x squared, which is n over c times delta 1. Maybe another, some different constant. Doesn't really matter. So the upper bound is a 1 over n times the delta. Delta is a fixed constant. So as n goes to infinity, this integral is less than n goes to infinity of n delta over c prime. Delta is a fixed constant. The capital N goes to infinity. So this one converges to 0, which is what we wanted. That if we avoid Fejer kernel is I don't know. So somewhere looks like this. And then if you avoid delta, then almost all mass is concentrated here as n goes to infinity. N goes to infinity, the area of this region converges to 0, as we can see from here. So by three properties, by those three oops, conditions, we have shown that the Fejer kernel is a family of good kernels. So this is we just approved it. Okay. All right, so this is all we have discussed. Let me recap what we have done. So today we talk about the Fejer kernel, that the sigma and fx was the Cesaromin. Then this can be written as fn convolution of fx. And then fn x can be written as 1 over n sine squared x over 2, numerator is a sine squared and x over 2. Second, we have shown that this is a family of good kernels. So that nice convergence of a Fourier series happens. So all those good properties happens for Fn. Okay. So these are what we discussed today, and then after spring break, we are going to talk about, just after the spring break, oops, we are going to learn another average. We are going to learn the Abel sum of the Fourier series. So this is a PR convolution of fx, and this is given by, so this looks like f hat n times e to the I n x. So we put this guy where r is between negative 0 and 1. As when r is a 1, this is the partial sum of the Dirichlet series, but r is less than 1, so this makes things a little bit smaller. And this is a key property of this Abel sum. And then because of this, then this we will show that this this is called a Poisson kernel, and this Poisson kernel is a also family of a good kernel, and then nice convergence happens. So this is what we are going to do after spring break. So over the break, if you have time, then or find the time to read the textbook about the next section. So we will continue. All right, so let's stop.